Okay, so in this chapter on capacitors, we're going to be looking at specifically capacitors in AC circuits. And what we have to look at here is get a little bit of an introduction to calculus, or something called the derivative. So in doing that, we're going to look at and analyze the capacitive AC circuits, explain why a capacitor causes a phase shift between voltage and current, define capacitive reactance. Then that falls into our definitions that we're going to need to see for the derivative and some calculus. Determine the value of capacitive reactance in a given circuit, and discuss instantaneous true and reactive power in a capacitor. So the derivative then, as it applies to the AC signal and the characteristics of in a capacitor, the derivative then of a time varying quantity, okay, the derivative and time varying quantity goes together, is the instantaneous rate of change. So we're looking at derivative being the rate of change in that quantity. Okay, you should also start thinking of this derivative or this rate of change as the slope of the line, because that's how the slope of the line is defined in your math experience. So the derivative. Current then as a derivative is defined as the rate of flow of charge, or the electrons, through the circuit. Instantaneous current, we use a little I instead of a capital I, can be expressed as the instantaneous rate of change of a charge. In this case now we use a lowercase q to characterize this, with respect to time, little t. So this expression I is equal to dq by dt is the definition of a derivative, the first derivative of the rate of change of charge per unit time. So this is the derivative of q with respect to time and represents the instantaneous rate of change of q. So in terms of instantaneous quantities, Q then is defined as the capacitance times a voltage. From the basic rule then of differential calculus, okay, this is the derivative of Q is dQ by dt. Take it one more step, and this is defined as the capacitance times the rate of change of voltage per unit of time. So since the current now, the rate of change, dq by dt, the current then can be also defined as the capacitance times the rate of change of the voltage, dV by dt. The instantaneous capacitor current then is equal to the capacitance times the instantaneous rate of change of the voltage across the capacitor. So we're looking at how things measure out in terms of changes per unit time. So this means that the faster the voltage across the capacitor changes, the greater the current. So what this is going to start to do is this is going to start to introduce something called phase changes or phase relationships between the current and the voltage in a capacitor. So as we proceed then in the next iteration here, the next video, I will start explaining what happens then and how these phase relationships start to change and vary.